Good morning and welcome to our second mathematics lesson. Today we're going to cover intervals of real numbers, Cartesian coordinates, functions, and then sigma notation. Before we begin, let me talk about the homework. Our first homework will be available later today. Previously, I said that each homework would be available for 7 days, but I'm concerned that some students might register late or have technical difficulties and might be disadvantaged. So I'm going to make a change. Now I'm going to set the deadline for every homework to be the 10th of January. Every week there will be a new homework, but every deadline will be the 10th of January. So if you really wanted to, you could wait until the 9th of January and then do all that homework. But because the homework is designed to help you learn each week, I encourage you to try to do one homework each week. Section 4 of this course is about intervals. What is an interval? An interval is a subset of the real numbers which satisfies two rules. First of all, the subset must contain at least two numbers, and rule number 2, this interval must not have any holes in it. For example, let's suppose we're looking at the set of all numbers x such that, this vertical line means such that, x is a real number and x is strictly greater than 6. I can draw a picture like this. If this line is the real numbers, then the blue part is this set. The set starts at 6 and it goes all of the way to infinity. Because the number 6 is not in the set, we draw an open circle at 6. The set has at least two numbers in. It has 7, 8, 9, etc. More than two numbers in here. And there are no holes in the middle of the interval. There's an open circle at the end, that's fine. There are no holes in the middle. So this is an interval. This set is also an interval. The set of all real numbers x, such that x is between -2 and 5. We can draw a picture of this interval like this. The interval starts at -2 and it goes to 5. Because -2 and 5 are in this set, we can draw a filled-in circle at -2 and 5. There are at least two numbers in the set. There's infinitely many numbers, in fact, in a set, and there are no holes in the middle, so this is an interval. This set is not an interval. The set of all numbers such that x is a real number and x is not equal to 0. This is not an interval because we have a hole at 0. We can classify a finite interval in 3 ways. We can say closed, half open, or open. A finite interval is closed if it contains both of its endpoints. It's half open if it contains only one of its endpoints, and open if it does not contain any of its endpoints. For example, if we look at this first picture, this is the interval from A to B, but we have open circles at A and B because A and B are not in the set. We can use notation. We can write the set as all of the numbers x, such that x is strictly between A and B. And we have a shorter notation for this set. We can write rounded bracket A, comma B, rounded bracket. Because these endpoints are not in the set, the set is called an open set. Or I might use the notation square bracket a comma b square bracket. This means the set of all numbers x, which are so that x is greater than or equal to a, but x is less than or equal to b. Here's a picture of this interval from a to b, but it includes a and it includes b. Because the endpoints are included, this is a closed interval. Or we might have a half open interval, either square bracket a comma b round bracket or round bracket a comma b square bracket. These two intervals include one of the endpoints, but not the other endpoint. So these two intervals are half open. For an infinite interval, we don't have this idea of half open. An infinite interval is either closed or open. It's closed if it contains a finite endpoint, and it's open if it's not closed. But there's one exception to this rule. The whole real line, all of R, we say is both open and closed. And we just say this so that more advanced mathematics makes sense. This is one of these unusual things that we need to do just so that later on maths still works. Some examples, some pictures. First of all, round bracket a comma b round bracket. It means all of the numbers x, such that x is strictly greater than a. Here's the picture. It's the interval from a to infinity that doesn't include a. This interval does not include its endpoint, so this is open. Or we might have square bracket a comma infinity round bracket. There's always a round bracket at infinity because infinity is not a number that we can include in our set, so always round brackets next to infinity. But all of the numbers x such that x is greater than or equal to a. This is the interval from a to infinity, but it includes the end a, so this interval is closed. We can do the same thing, but between minus infinity and some number b. First interval is open, the second one is closed. And then finally, exception to our rule, the whole real line, interval from minus infinity to infinity, which is another way of writing all of R. This interval is both open and both closed. Draw the picture, it's just a line that goes all of the way from minus infinity to infinity. We can combine two or more intervals using the union notation that we talked about last week. For example, this is a picture of closed interval from minus 8 to minus 2, union with the closed interval from 2 to 8. That's all we need to do about intervals. Chapter 5 is about Cartesian coordinates. Cartesian coordinates are ways to explain the position of a point in a two-dimensional plane. We start with two lines, a horizontal line, which is called the x-axis, and a vertical line, which is called the y-axis. The point where these two lines cross is called the origin. Then we can explain the position of all of the points in the plane using two numbers. For example, if I want to describe the position of the point P. To get to P, we can start at the origin. We can go to the right by 4 units, and then we go up by 3. We describe the position of this point using the numbers 4 and 3. Or, for example, point Q with coordinates -2, 4. Minus number means go left, we go left 2, and then 4 means we go up. Starting at the origin, left 2, up 4, we get to -2, 4. The set of all points in the plane, all of the points x and y. We have a number x, which is a real number. We have another number y, which is a real number. So we have all the numbers in R, and again, all of the numbers in R. We denote this by R squared because we have two numbers in R. You see something like this. You look at the number, and this tells us that we are in a two-dimensional space. And as I said on the previous slide, the point 0, 0, or the point O, is called the origin. For example, let A, 2, -1, and 3, 1 be points in R squared. Draw the triangle OAB. First, we can plot the point A. 2 -1 means go right 2 and then down 1. Come to this point. Point 3, 1. Right 3, up 1. Come to this point. Point O is the origin. Draw the triangle with vertices at these 3 points. We get this triangle. Or you might be asked, draw the region of all points which satisfy x is between 1 and 3. First, we can look at x is greater than or equal to 1, or to simplify this, we could look at x equal to 1. This is a vertical line of all of the points where x is equal to 1. Then we can look at the second inequality, x is less than or equal to 3. Let's simplify this first of all to x equal to 3. All of the points where x is equal to 3. We're asked to draw all of the points where x is between 1 and 3. So in other words, we're drawing all of the points between these two vertical lines. Or perhaps I say, draw the region of points which satisfy x is between 1 and 2 and y is between 1 and 3. First look at x and 1. We have a vertical line. Then x2, again we have a vertical line. Y equal to 1, we have this horizontal line where all of the points are equal to 1. Y equal to 3, we have another horizontal line. We're asked to draw the region of points where x is between 1 and 2, in other words, between these two vertical lines. Y is between 1 and 3, between these two horizontal lines. In other words, we have this rectangle here. We can talk about the distance between 2 points. Let's suppose I have 2 points, a point P1 and a point P2. Point P1 has coordinates x1 and y1. Point P2 has coordinates x2 and y2. The length of this horizontal line is the difference between x2 and x1, the absolute value of x2 minus x1. And the length of this vertical side is the absolute value of y2 minus y1. The length of this diagonal line, in other words, the distance between P1 and P2, we write like this. 2 vertical lines, P1, P2, 2 vertical lines. And because this is a right angle triangle, we can use Pythagoras to find a formula for the distance between P1 and P2 in terms of x1, x2, y1, and y2. Of course, using Pythagoras, the distance between P1 and P2 is given by this formula. Square root of x2 minus x1 squared plus y2 minus y1 squared. For example, I might ask you to calculate the distance between point 13 and point 4 minus 1. We put the numbers into our formula. We have x2 is 4, is x2. We have x1 is 1, so we have 4 minus 1. y2, we have minus 1, and y1 we have 3. So in the second bracket we have minus 1 minus 3 all squared. And when we calculate this, we find that the distance between A and B is 5. Section 6, which is our big topic for today, is the concept of functions. A function, we're going to be writing them like this a lot. We read this in English as y is equal to f of x. In this notation, f denotes the function, x is the independent variable, and y is the dependent variable. In other words, x is the number that we can choose any number that we want within some constraints. And after we calculate f of x, we determine y. Y is determined by f and x. Let me start with a formal definition. What is a function really? A function from a set D to a set Y is some rule which assigns a unique element of Y to each element of D. The set D, which is where we start, is the set of all possible values of x. This is called the domain of f. Set Y, the set that we end up in, the set containing y, containing small y, is called the target of f. And the set of all possible values of f of x is called the range of f. If we have a function with domain D and target y, we can write the function like this. F is a function from D to y. Two examples. First of all, f might be the function with domain real numbers and target real numbers, and the formula f of x equals x squared. Or we might have a different function. F is the function with domain open interval from minus infinity to infinity. But that, of course, that's just the same as the real numbers. But now I've made a change. Now the target is only the non-negative real numbers, the closed interval from 0 to infinity. And same formula, f of x is equal to x squared. These are two different functions because they have a different target. You might think of a function like this. We have two sets, D and Y, and the function maps each number in D to some number in capital Y. So we have some number x, and the function then gives us some number f of x. Or if we have some number t, the function gives us some number f of t. And we can do this at every single number in D. After we've done this, we can look at all of the possible values of f of x. This dotted line, which will be a subset of capital Y. The region inside this dotted line is called the range of f. Or we might think of a function in a different way. We might think of a function as some sort of machine. Put a number x into the machine, and we get a different number f of x out of the machine. I'm going to run through some examples now. First of all, y is equal to x squared with the domain from minus infinity to infinity. I'm interested in what is the range of, what is the biggest number or the biggest concept that we could get. If we take either infinity or minus infinity and then we square it, we get infinity. So it's possible to get infinity. Is it possible to get, for example, 1? The answer is yes. I could take number 1, 1 squared is equal to 1. Number 1 is in the range. Is the number 0 in the range? And the answer is yes, because 0 squared is equal to 0. So 0 is in the range. What about a negative number, for example, minus 1? Minus 1 in the range. Is it possible to have minus 1 is equal to x squared, for x a real number? And the answer is no. The smallest possible number that we could make, smallest possible value of y is 0. So the range must be interval from 0 to infinity. Another example. Y is equal to 1 divided by x, where our domain all of the real numbers except 0. What sort of numbers can we make? Possible values of y are there? Is it possible, for example, to make 7? Is it possible to have 7 equal to 1 over x? And the answer is yes. We could have x is 1 divided by 7. So 7 is okay. Is it possible to have, let's say, 1 million? Yes, x could be 1 divided a million. Is it possible for y to be equal to, say, minus 2? And the answer is yes. We could choose x as minus a half. Is it possible for y to be equal to 0? No, it's not possible to find some x such that 1 divided by x is equal to 0. The range of y, all of the possible values of y, there's a mistake here, this should be y. Y here and y here. All of the possible values of y except y equal to 0. What about square root of x? We can choose which domain we want. I choose the closed interval from 0 to infinity. What possible values of y do we have? We can have any number between 0 and infinity. Next one. If x is between minus infinity and 4, what possible values of y do we have? Well, if we take 4, for example, if we put 4 in here, we get square root of 4 minus 4, which is 0. If we take minus infinity and we put this in here, 4 minus infinity is 4 plus infinity or infinity. Square root of infinity is infinity. Range of y, all of the possible values of y, is the interval from 0 to infinity. Y equal to the square root of 1 minus x I'm choosing the closed interval from -1 for my domain. And then I'm asking what possible values are y. I suppose, first of all, we take 1. 1 minus y squared, which is 0. What about if we take -1? 1 minus -1 squared is again 0. What about if we take some number in the middle? I suppose we take 0, which is in the middle of this interval. 1 minus 0 squared, which is 1. If you think about this, if x is some number between -1 and 1, y must be a number between 0 and 1. 3 more examples. These are all y is equal to x squared, but I'm choosing to use different domains. Let me pause for a moment so you can think what I'm going to write here. If the domain is 1, 2, 2 infinity, or minus infinity, minus 2. First of all, if x is between 1 and 2, y must be between 1 and 4. That's straightforward. And if x is between 2 and infinity, then y must be between 4 and infinity. For the next one, remember we're squaring it. Minus infinity squared is infinity. Minus 2 squared is 4. So again, y must be some number between 4 and infinity. And the final two examples, 1 plus x squared remain half open interval from 1 to 3, and y is equal to 1 minus the square root of x for x between 0 and infinity. I will pause for a moment. If x is between 1 and 3, x squared must be between 1 and 9, so 1 plus x squared must be between 2 and 10. And of course it's closed at 2, open at 10, because our domain is closed and open. 1 minus the square root of x. This is the interval from minus infinity to 1. If we use 0, we get 1. If we use infinity, we get minus infinity. So y must be between minus infinity and 1. We can talk briefly about graphs of functions. The graph of a function f is the set containing all of the x, y, which satisfy the equation y is equal to x. This is the formal definition of the graph. For example, graph the function y is equal to 1 plus x squared over the interval from minus 2 to 2. First thing I'm going to do is I'm going to make a table of some points that satisfy this equation. I'm choosing to use these values of x, minus 2, minus 1, 0, 1, 3 over 2, and 2. And then for the value of x, I've calculated y. For example, if x is minus 2, y must be 5. If x is minus 1, y must be equal to 2, etc. Step 2, plot these points on a graph. For example, the point where x is minus 2 and y is equal to 5, or the point where x is 3 over 2, y is 3 and a quarter. And then draw a smooth curve through these points. This is the graph of 1 plus x squared between minus 2 and 2. Vertical line test. Not every curve that we can draw is a graph of a function. Look at the left picture first of all. 1 plus x squared, which we just drew. If I drew a vertical line, the vertical line is going to intersect the graph at 1 point. This is because the blue curve is the graph of a function. For example, if I drew a circle and then a vertical line, the vertical line would intersect the circle at 2 points. This tells us that a circle is not the graph of a function. Vertical line test says a vertical line intersects the graph of a function at most 1 point. So, for example, if a is some number in the domain of our function, the vertical line x equal to a will intersect the graph of f only at point a, f of a. I want to talk briefly about piecewise defined functions. Instead of using the same formula on all of the domain of a function, we might have more than one formula. For example, the function absolute value of x is equal to x if x is a positive number, or minus x if x is a negative number. We're writing this function in this way with different formulae in different parts of the domain. Or another example, suppose f of x is the function which has the formula minus x, and x is strictly less than 0. F of x is equal to x squared if x is between 0 and 1, and f of x is equal to 1 if x is greater than 1. If we drew the graph of this function, it looks like this. First, a bit of x, and then a bit of x squared, and then a part of 1. When we do calculus, we're going to be interested in increasing and decreasing functions. Suppose capital I is an interval and f from I to r is some function. The function f is called increasing if it's always going up. In other words, if whenever we have two numbers x1 and x2, where x2 is bigger than x1, we must also have the function that x2 is bigger than the function is x1. The function is called decreasing if it's always going down. Same as in increasing, but instead of less than, we changed greater than. Some pictures. This function, as we move from the left to the right, the function is always going upwards. This function is an increasing function. This function is a decreasing function. As we go from the left to the right, the function is always going downwards. So this function is called decreasing function. This function goes up, down, up, down, up, down. It's not always going upwards, so it's not increasing. This function is not always downwards. This is not a decreasing function. We can classify functions as even or odd. Let me just remind you. Numbers 2, 4, 6, 8, and 10 are even numbers, and the numbers 1, 3, 5, 7, 9, etc. are the odd numbers. We can call a function even or odd as well. An even function the rule is we must always have that f of minus x is equal to f of x. For an odd function, we have a very similar rule. The rule is that f of minus x must be minus f of x. Let's do some examples. First of all, f of x is equal to x squared. To understand this, we start with f of minus. F of minus x is minus x squared, which is the same as x squared, which is f of x. We have that f of minus x is equal to f of x, so this function is an even function. In terms of pictures, you can imagine that we put a mirror down center of the picture. Let's suppose we can put a mirror on the y-axis and then ask, is the left side exactly the same as the right side? If the answer is yes, then we have an even function. Next, the function x cubed. Again, to understand this, we start with f of minus x. And as we go along the calculation, we find that this is equal to minus f of x. So this is an odd function. In terms of pictures, what does an odd function mean? It means we can take the graph and we can rotate the graph 180 degrees about the origin, and we have exactly the same graph. Anytime you see a graph that we can rotate 180 degrees and still have the same graph, you have an odd function. Next example, x squared plus 1. Is this an even function, an odd function, or neither even nor odd? Understand, we always start with f of minus x. And with the calculation, we find that this is the same as f of x. So this is an even function. What about x plus 1? Is this even or odd? Neither. This one I'll do slightly differently. Instead of looking at every single x, I'm just going to look at one number. I'm just going to look at minus 2 and 2. G of minus 2 is equal to minus 1, and we can calculate that G of 2 is equal to 3. These are not the same. Minus 1 is not equal to 3, so it's not an even function. But minus 1 is also not equal to minus 3, so it's not an odd function. This function is not even and it's not odd, neither even nor odd. If we need to prove that a function is even or a function is odd, we have to do it for every x. If we want to prove that a function is neither even nor odd, we only need to do it for one number. Just choose some number, I choose the number 2, calculate the function at the number and the function at the minus of that number. Are they the same or are they negatives? Now I'm going to run through some different types of functions very quickly. Linear functions are straight lines. This is where linear comes from. It's the word line or straight line. Linear function has the formula mx plus b for some numbers m and b. Here are some examples. For example, this blue line is m equals minus 2, b equals 1. This is the function minus 2x plus 1. Power function. Well, the power function is a function of form x to the power x for some real number a. In English, we read this notation as x to the power of a. I'm going to show you some pictures of common power functions. First of all, y is equal to x. This is a power function a equal to 1. Y is equal to x squared. Y is equal to x cubed. Y is equal to x4. This looks similar to x squared, but it's more squashed down. This is x squared. X to the power 4 is squashed down somewhat. We might have negative numbers. For example, a to the power minus 1, x to the power minus 1, which is the same as 1 divided by x, like this. Or we might have fractions. X to the power of a half, which is the same as the square root of x, looks like this. X to the power of 1/3, or the cubed root of x. X to the power 3/2, that means square root of x cubed. X to the power 2/3. Look at the previous one, this one. This was x to the power 3/2. The shapes are similar but flipped. Polynomials. A polynomial looks like this. Some number an, and then a power function x to the power n. Some number a to the power n minus 1. Power function x to the power n minus 1, plus etc. All the way down to some number a2 x squared plus some number x plus some number a0. These a numbers are all real numbers. N is either a natural number or 0. So in other words, it's 0, 1, or 2, or 3, or 4, etc. The domain of a polynomial, in other words, the biggest possible domain of a polynomial, is always the whole real. Polynomials are defined everywhere. And as long as this number n is strictly positive and an is not equal to 0, then n is called the degree of a polynomial. If we take two polynomials, p and q, and then we take the quotient of p divided by q, this is called a rational function. For example, 2x minus 3 is a polynomial. 7x plus 4 is a polynomial. When we do polynomial divided by polynomial, we get a rational function. The exponential functions are the functions of the form a to the power x, where a is a strictly positive real number which is not equal to 1. I've drawn some graphs of exponential functions here. Again, the largest possible domain of an exponential function is always the whole real line. The inverse of an exponential function is called a logarithmic function. For example, if we know that x is equal to a to the power y, and then we want to do the inverse, we get the logarithmic function log base a of x. In English, I'm reading this as log base a of x. Again, a is a positive real number which is not equal. If we go back, look at this graph, and then let's suppose that suppose there's some diagonal line here. We're holding this line, and then we're going to flip it. Then we get graphs which look like this. These are the same curves as on the previous slide, but flipped over because they're inverse functions. Before we do calculus in the last 4 weeks of the term, we need to discuss angles. There's two common ways, I should say, to measure angle. We could use degrees or we could use radians. Degrees we learn about in high school, but what are radians? To understand, first let's look at this circle. Let's suppose I have a circle of radius 1. And let's suppose I have some angle. This angle just here. How can we measure this? We could use degrees. We could measure the angle here and write it in terms of degrees. Or what we can do is we can measure the distance around the outside of the circle. This distance around the outside of the circle is the angle in terms of radians. So, for example, look at the second picture. I have half a circle. We know that this angle in the middle of the circle is 180 degrees. And we know that the distance around the outside of the circle, the distance around the outside of half of a circle of radius 1 must be pi. So 180 degrees is the same as pi radians. Pi radians is the same as 180 degrees. We divide by pi and say that 1 radian is the same as 180 divided by pi degrees. Or we might divide by 180 and say that 1 degree is the same as pi divided by 180 radians. Three very common angles. 45 degrees is the same as pi over 4. 60 degrees is the same as pi over 3. And 90 degrees is the same as pi over 2. Note that when we use degrees, we have to use a little circle. Say we use degrees. When we use radians, we do not use a symbol. Anytime you see an angle which does not have a little circle, the angle will be in radians. In calculus, we must use radians. When we get to part 4 of this course, when we're doing calculus, anytime you see an angle, the angle will be using radians. And this is because calculus does not work if we use degrees. To do calculus, we must use radians. The trigonometric functions, sine, cosine, tangent, etc. Hopefully it's revision for you. Start with a circle of radius r and measure the angle from the x-axis to some ray, this green line. Look at the point where the line intersects the circle and then take its x-y coordinates. You can find the sine function, sine of theta, to be divided by r, and the cosine function, cos of theta, x divided by r. After we have sine and cosine, we can define the other 4 functions. Tangent function, tan of theta means sine divided by cos. Secant function means 1 divided by cos. We can remember this because we have c and c. The cosec function, there's 2 different ways to write this. We might write COSEC or we might write CSC. I prefer the first notation. I'm going to be using the first notation in this course, but some books you find using the less common notation CSC. Cosec is 1 divided by sine, and cotan means 1 divided by tan. There's one more thing to note. These are only defined as long as we're not dividing by 0. So, for example, if cos is equal to 0, we can't do divide by 0. Tan is defined when cos is not equal to 0. Likewise, sec is defined when cos is not equal to 0. Cosec is defined when sine is not 0, as is cotan. Let's look at some very common results. First of all, this triangle, a right angle triangle of length 1, 1, and then by Pythagoras, this side must be the square root of 2. And I'm interested in the angle pi divided by 4, or 45 degrees. We know that sine is 1 divided by r. Is y, is r. Sine must be 1 divided by root 2. Cos is x divided by r. So cos pi over 4, or cos 45 degrees, must be 1 divided by root 2. After we know these two, we can do the other 4. Tan of 45 degrees, or tan of pi over 4, is sine divided by cos, or 1. Sec is 1 divided by cos, root 2. Cosec is 1 divided by sine, that's root 2. And cotan is 1 divided by tan, 1 divided by 1. Another common triangle. Let's suppose we start with equilateral triangle of side 2, and then let's suppose that we cut the triangle in half. Get this triangle. And we know this side must be 2, this side must be 1, because we've cut it in half. And using Pythagoras, the final side must be the square root of 3. I'm interested in this angle just here. The angle pi over 3, or 60 degrees. Using this triangle, we can do sine. That's y divided by r, or root 3 over 2. Cos is x divided by r, or half. And then I'll leave the other 4 for you to look at later. These are the graphs of sine and cosine. Final topic today is the topic of sigma. We're going to need sigma notation both when we do probability and when we do calculus. So let me introduce it now in the introduction. I suppose I have lots of numbers and I want to add A1 plus A2 plus A3 plus A4 plus A5, etc. all of the way up to plus AN. Instead of writing it in this very long way, we have a nice small way to write this. You can write this as capital sigma from k is equal to 1 to n of ak. In this notation, this symbol is the Greek letter capital sigma. K equal to 1 at the bottom says the sum starts at A1, and the n on the top says the sum stops when k is equal to n. We stop at an. Some example. I suppose I wanted to do 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 plus 8 squared plus 9 squared plus 10 squared plus 11 squared. Instead of writing this in this long way, I could write the sum from k equal to 1 to 11 of k squared. Or instead of writing f of 1 plus f of 2 plus f of 3, all of the way up to f of 99 plus f of 100. Instead of writing this very long thing, I could just write the sum from k equal to 1 to 100 of f of k. The sum k is equal to 1 to 5 of k means start at k equal to 1, so start at 1, and then do plus 2, plus 3, plus 4, plus 5, and then when we get to 5, we stop. This is 1 plus 2 plus 3 plus 4 plus 5, or 15. Some more examples. The sum from k is equal to 1 to 3 are minus 1 to the power k multiplied. We start at k equal to 1, so we start by putting 1 instead of k. That's minus 1 to the power 1, and then 1. And then we do k equal to 2, minus 1 to the power 2, and then 2. And then we do k equal to 3, minus 1 cubed, multiplied by 3. And 3 on the says, when we get to 3, we stop. We have minus 1 plus 2 minus 3, which we can calculate minus 2. Or the sum from k is equal to 1 to 2 of k divided by k plus 1. Start with k equal to 1, 1 over 1 plus 1, then go to k is equal to 2, 2 divided by 2 plus 1, and then we stop. If we calculate this, you can check this is 7 divided by 6. And one more, which I will leave you to check later. We don't have to start at 1. If we wanted to, we can start at k equal to 4. Now, final example for today's lesson. I want to find the formula for 1 plus 2 plus 3 plus 4 plus 5, etc. All of adding up all of the natural numbers up to the natural number n. First of all, I'm going to instead find a formula for double this, 2 multiplied by this number. And what I do is I do 1 plus 2 plus 3 plus 4 plus 5 for the first of these. And then for the second one of these, I'm going to write them in the opposite order. Instead of 1 plus 2 plus 3, I'm going to start with the biggest number, n plus n minus 1 plus n minus 2 plus n minus 3, etc. and finish at 1. I've added all of the numbers between 1 and n up twice. So I have 2 multiplied by this number I want to find. Now, look at each column. I've written it this way for a reason. The first column I have 1 plus n, or 1 plus n, okay. Then I have 2 plus n minus 1. Again, that's n plus 1. And then I have 3 plus n minus 2. That's just n plus 1. If you look along, you can see that in each column we have n plus 1. So really we're doing n plus 1 plus n plus 1 plus n plus 1 plus 1, etc. How many n plus 1s do we have? We have n of them. So we have n multiplied by n plus 1. To finish, we can divide by 2. Sum from k is equal to 1 to n of k is n multiplied by n plus 1 divided by 2. We will need this formula when we do calculus. Two more formulae we will need when we do calculus. The sum of the first squared numbers is given with this formula, n plus 1, 2n plus 1 divided by this. And the sum of the first n cubed numbers is n plus 1 over 2, all squared. We will need these formulae in the last few weeks of term when we do calculus. And this is the end of today's lesson. Next week, we're going to start talking about the geometry of space. We will cover polar coordinates, conic sections, and then three-dimensional Cartesian coordinates. Do you have any questions? The lecture notes I'm using is available through OLearn. If you look in OLearn under the course material section, which should be the first one you see when you log in, if you're using a computer, you will see the syllabus and the lecture notes listed on that page. Okay, I'm going to take a 10-minute break now, and then I will come back and see if there are any more questions. If you don't have any questions, you're welcome to leave the classroom now. If you think of a question later, you can ask it in the discussion board, and I will answer it there after I see it.